All right, so welcome to the lecture series on Introduction to Computer Networks. So today we're going to cover the topic of data representation and specifically the number systems that we have for computing. So computer data, as we have already mentioned, is always stored as binary numbers. So what happens is that any form of information that you would like to process with computers or store in a computer needs to be converted into binary number form. The types of data that we could have are numeric data. It could be whole numbers, positive or negative numbers, decimal numbers. It could be texts, letters from the English alphabet, from any other alphabet, special characters that we have in any language. And it could be multimedia. That is, it could be audio, image, video. So no matter what the type of data is, it must be converted into a stream of binary numbers, which are basically zeros and ones, and only then it could be stored and retrieved by computers. So when we need to store data, a binary number is a bunch of ones and zeros, and they are stored in many different forms of hardware. For example, if you look at a CD, it looks exactly flat, right? It looks a perfect flat disk. However, there are microscopic ridges which are there in the CD which hold these zeros and ones in the form of binary data. Hard drives that you have in your computers, they have magnetic plates which store the binary ones and zeros in the form of magnetic charges. USB drives, they have tiny circuits which store charges. So a charged value means 1 and a not charged value means 0. So no matter what kind of storage that you use, everything needs to support the storage of zeros and ones to represent the stored information. So when we're talking about number systems, we refer to basically three different types. First of all, decimal numbers are the numbers which we generally use as humans. The numbers are represented using digits starting from 0 till 9, and that is a total of 10 digits. So therefore, decimal numbers are referred to as base 10 numbers. On the other hand, binary numbers are represented using the digits 0 and 1. So the number of options for the digits we have is 2. So therefore, this particular numbering system is referred to as a base 2 number system. Third, computers or data in computing is also represented using hexadecimal numbers. So hexadecimal means 16, and the digits that we have in hexadecimal numbers are 0 through 9, which is 10, and then A through F, which is 6. So 10 and 6, a total of 16. So that is what we call a base 16 number system. So in regular life, everyday life, humans generally use decimal numbers, 1, 2, 5, 6. Binary is something that, or hexadecimal is something that, humans don't really use in everyday life. However, if you're looking at computers, computers don't understand decimal or hexadecimal. It only understands binary. The reason we have some use of hexadecimal numbers is because of some specific networking applications and addressing, and that is something that we'll cover in the later chapters. But in terms of the number system, this is something that we have to understand, and that is why this chapter includes hexadecimal. So if you look at the way that we can count in these three numbering systems, so decimal is a base 10, so you have got 0, 1, 2, 3, 4, 5 through 7, 8 through 9, 10 through 15, 16, 17, and then to 23. In binary, you only have an option of 2 digits, right? 0 and 1. So a 0 is a 0, then a 1 is the next increment 1. Next, you go 1, 0, and then 1, 1. Then you're basically increasing the number of places, and then you change the numbers from 0 to 1, and then you go to the next larger number from 2 digits to 3 digits to 4, and so on and so forth. So it's 101, then 110, 111. Then when all of these are 1, the next number is 4-digit long, so 1 and then 3 zeros. Then the last digit over here changes to 1, then 10, 11, then 3 digits again, 100. Sorry, 4 digits. The third digit changes to 1, and then 1101, so on and so forth. So something that you don't really need to understand, but the progression is something. It's something that you don't need to memorize, but the progression is something that you do not understand. All right. So the next thing is with hexadecimals. It gets kind of interesting because we are now using 16 options for the digits. So we go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is A. So a decimal 10 is hexadecimal A. A decimal 11 is hexadecimal B. Decimal 12 is hexadecimal C. 13 is D. 14 is E, and then 15 is F. So in addition to 0 through 9, we now have 6 more digits to represent a total of 16 numbers with the 16 digits. And then if you go on, so it changes to 1, 0, and then the 1 is fixed here, so 0, then 1, 2, 3, 4, 5, 6, 7, and it will keep on going, so on and so forth. So the way that we represent these numbers or write out these numbers is something that should be useful. So decimal, we've already mentioned that it is a base 10 number, and the way that we write it is 6 with a subscript of 10, 15 with a subscript of 10. This would mean that the 6 is a base 10 number. 15 is a base 10 number. Binary, these are base 2 numbers, and we put a 2 as a subscript. So 110 is not 110, but rather it is 110 in base 2. So just to clarify, 110 in base 10 is not the same as 110 in base 2. They are completely different numbers. Next, hexadecimals. These are base 16, so we put a small 16 as the subscript. So 6 with a subscript of 16 means that this is a base 10 number. So these are basically the same numbers. So 6 base 10 is the same as 110 in base 2 and 6 in base 16. 15 in base 10 number is the same as 1111 in base 2, which is equals to F in base 16. So given that we now understand what these three number systems or three bases for the number systems means, we now will look at how we can convert each of these number systems to another. So before we go there, I just want to explain how numbering is actually generated, and the best way to exemplify is using a base 10 number because it's a decimal and it's something that we use every day. So let's say the number 125. So what this means is that the 5 is in position number 0, the 2 is in position number 1, the 1 is in position number 2. So 5, then 2, and then 1. So the positions go from right to left in 0, 1, 2 increasing sequence. And for each of these numbers for the given position, we multiply it with the base. So the weight is basically the position of each digit, and the base is the base of that numbering system. So 10 to the power of 0 is 1, so 5 times 1 is 5. 10 to the power 1 is 10, so 2 times 10 is 20. Then 10 to the power 2 is 100, so 1 times 100 is 100. And then if we add these numbers, we get 125. So that is how we can generate numbers, and that applies for any numbers and any base system. So let's start with the conversion of binary to decimal numbers. So the process is that we multiply each bit by 2 to the power n, where n is the weight of the bit, which means the position number of the bit. It starts from the right, starting at 0, and the rightmost bit is called the least significant bit or LSB, and the leftmost bit is called the most significant bit or the MSB. So once we have done the multiplications for all of the binary digits, we then add the results. So let's look at how this works out. So let's say we have the number 101011 in base 2, and we need to convert this to base 10, which is a decimal number. So we can first write it out. The binary is 101011 right here. Next, we look at the positions of the bits. So 0, 1, 2, 3, 4, and 5, starting from right to the left. The values for the weights we use in terms of powers of 2 because this is a base 2 number. So 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32. Next, we basically look at the bits which are ones, and we only consider those values. So this 1, this 1, this is 1, and this is 1. So if you see here, we would now add 1, then 2, then this multiplied by 0 becomes 0. Then we get 8. Next, multiplied by 0 becomes 0. And then 32. So if we add all of these, we get 43. And we write the subscript of 10 to show that this is a base 10 number. So let's look at another example. I have laid it out in a different way so that whoever feels comfortable when doing the math, you can use either way in a layout that you want. So let's say we have the number 100111100, and this is a base 2 number, and we want to convert it to a decimal. So first you write it out, 100111100. Next, based on the positions, so this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. We write out these values. And next, we take the ones which have the 1 bit. So the decimal of this binary would be 4 plus 8 plus 16 plus 128, which is equals to 156. So the progression of binary is similar to the way that we count numbers in decimals. It just might be a little different because we are working with 2 digits here, but once you get the hang of it, it just gets very easy. So when you have only 1 bit, you have 2 options. It's either 0 or 1. When you have 2 bits, you have 4 options. You have 0, 0, then 0, 1. Basically, you are changing the first bit position, and then 1, 0 and 1, 1, where you change the second bit to 1 and then change the first bit from 0 and 1. The numbers are equivalent to decimal 0, 1, 2, and 3. If you have 8 different bits, the combinations are, if you have 3 different bits, there are a total of 8 different combinations. So the way that it works is basically you have 0 and then 1, 0, 1, 0, 1, 0, 1. This is for the first bit. For the second bit, you have 0, 0, and then 1, 1, 0, 0, 1, 1. For the third bit, you have 0, 0, 0, 0, 1, 1, 1, 1. So if you see here, the way things are changing is that in the first bit, it's 0, 1, 0, 1, 0, 1, 0, 1. For the second bit, it's changing every 2. And then for the third bit, it's changing every 4. The decimal equivalent values for these 8 different binary numbers would be 0, 1, 2, 3, 4, 5, 6, and 7. So the thing that you need to grab here is that if you have 3 bits, you can represent a maximum of 7 in terms of the decimal value, which is 3 ones. So the general rule here is that if you have 1 bit, we have seen that there are only 2 options. When we had 2 bits, we saw that there were 4 options. So the formula is basically for n number of bits, there are 2 to the power n different binary numbers. So let's say if we have 7 bits, that would be 2 to the power 7 equals 128 different binary numbers. If you have 10 bits, you have a total of 1024 different binary numbers. So the smallest binary value, irrespective of the size of the binary number, would be all zeros. So let's say if we have 5 binary digits, and if all of them are zeros, the decimal equivalent is 0. If we have 2 bits, if we have both of them as 0, the decimal value is 0. So the idea is that for the smallest value, you just need to set all the bits to 0 and you get the smallest value. The largest value is just the opposite. No matter how many bits you have, let's say 6, if you set all of them to 1s, that is the maximum value for 6 bits. And the decimal value for that you can get using the formula 2n minus 1. So if we have 4 bits, 2 to the power 4 minus 1 is 15. Same way, if we have 8 bits, 2 to the power 8 minus 1 is 255. So the maximum decimal value would be 255. So next, we look at the way that we can convert a decimal number into a binary number. Method 1 is where we look at the division approach. So the way we do it is we keep on dividing a number by 2 and we have to keep track of the remainder for each of the divisions. And the way the binary number is generated is that the first remainder that we get from the division is going to be our least significant bit. The second remainder is going to be the next, and so on and so forth. So let's see how this works out. So let's say we have 125 in a base 10 number, and we would like to find the binary equivalent for that. So 125 divided by 2 is 62 with a remainder of 1. 62 divided by 2 is 31 with a remainder of 0. 31 divided by 2 is 15 with a remainder of 1. 15 divided by 2 is 7 with a remainder of 1. 7 divided by 2 is 3 with a remainder of 1. 3 divided by 2 is 1 with a remainder of 1. And then 1 divided by 2 is 0 with a remainder of 1. So therefore, we say the number is going to be generated by taking the first remainder to be the least significant bit and in reverse order. So it's 1, then 0, then 1, 1, 1, 1, 1. And this is our equivalent binary number for 125. So next, we look at a second method in which we can convert a decimal into a binary number. So for that, we first need to estimate how many bits we need for that given decimal number. And it is an estimation that you can make pretty easily based on the max value that we have for each binary number. And if we just take a look at this is the slide that I'm referring to. So for 6 bits, the maximum value that you can represent is 63. With 7 bits, the maximum number that you can represent is 127. So in method 2, first we estimate the number of bits, and then we start by laying out a table. So we track the values. So these are going to be our binary bits, and these are the values of each of the positions, which are basically powers of 2. So 2 to the power 0 in the least significant bit on the right, and 2 to the power 6, which is 64, as the most significant bit on the left. After that, we start with the leftmost bit here, and we keep on checking with the value that we are trying to convert, and we compare it and see if it is greater than or less than or equal to the number for that position. So if the position value is greater than the number that we have, we mark that position as 0. If the value of the position is less than the number that we have, we mark that bit in that position as 1. and we subtract the value of that position from the decimal number that we are trying to convert. If the value of the position is equal to the number that we have, we make the binary digit in that position as 1, and we mark the rest of the binary bits to the right as 0. And we keep on doing this until and unless we have marked all the binary bit digits that we are trying to convert. So let's look at an example. So let's say we have 106 as a base 10 number and we are trying to convert it to the binary. So if we have 6 binary bits, the maximum decimal value that we can represent is not enough because that is less than 106. So we need 7 bits because 6 is not enough. Then we create our table where these would be our binary digits, and we put these values for convenience, which are basically the powers of 2. So first, we start from the leftmost. The value of the position is 64, and our number is 106. So 64 is less than 106. So therefore we mark it 1 and we subtract 64 from 106. We are now left with 42. So we take 42 and we now check the next bit. The next bit is 32. Our number is 42. So 32 is lesser, so we mark this bit as 1 and we subtract 32 from 42. Our number is now 10. The next bit that we have, the value of that is 16, and 16 is greater than 10. So we mark this as 0. We now go to the next position, which is 8, and our number is 10. So 8 is less than 10, so we mark this as 1, and we subtract 8 from 10, we are left with 2. So 2, in the next position we have a value of 4, so 2 is less than 4, 2 is greater than 4, so we mark this as 0, and we go to the next position. The next position, the value is 2, our number is 2, and these are equal. So we mark this as 1 and we mark all the rest as zeros. So in this case we only have 1. If we had more left, all of them would turn into 1s till the least significant bit. So the number that we have generated is going to be 1101010. This is the equivalent of the number that we have converted.